Good day everyone, welcome to the video lecture about rotational and vibrational spectroscopy. You may have learned about the electromagnetic spectrum from the previous video lectures. EM spectrum is basically the full range of the electromagnetic radiation organized by frequency or wavelength, in which the spectrum is divided into separate bands with different names for EM waves within each band. One of the essential applications of the electromagnetic spectrum is the spectroscopy. As shown here, the visible and ultraviolet region is responsible for analyzing the transition of electrons from one energy level to another, in which it gives the information about the atomic structure. An example of spectroscopy instrument applied for this region is the UV spectrometer. On the other hand, the microwave region can analyze the transition in rotational levels, in which it gives information about the polarity of the bonds. Here is an example of the microwave spectrometer. While infrared region analyzes the transitions in molecular vibrational levels, which gives the information about the types of bonds or bond order. The spectroscopy instrument used for this is the Fourier transform infrared spectrometer. But for this discussion, we will be only focusing on the concept of rotation and vibrational spectroscopy. One of the most important techniques in studying the vibration rotation information is the Raman spectroscopy. In spectroscopy, an atomic or molecular system having a certain wave function and energy either absorbs or emits energy, usually in the form of light, and in doing it, so it becomes described by a different wave function and energy. The selection rule formally constrains the possible transitions of a system from one quantum state to another, in which it describes how the probability of transitioning from one level to another cannot be zero. The law of conservation of energy requires that the light, that usually comes in the form of a single photon, have the same energy as the difference in the energy of the initial and the final states. This one here is called wave function, and as we review, the wave function is the energy required to remove a single electron. This equation here is written in the original form of the Bohr frequency condition. The difference in the energy of the two quantum states is equal to the energy of the photon, which is also equal to the Planck's constant and the frequency of the photon. Quantum mechanics defines a specific expression called a transition moment, in which irreducible representations can be applied. For an absorption or emission of a photon, the transition moment m is defined as the integral of the final state and initial state, and which mu hat is the electric dipole moment operator. E is the charge of particle, and x sub I, y sub I, and z sub I are the coordinates of the particle. Transitions of this sort are electric dipole transitions. Transitions between the wave functions can be prompted by other interaction like magnetic dipole or polarization changes, but electric dipole transitions are the most common. In order for the integral in the equation to have a non-zero numerical value, the irreducible representations of the three components of the integrand must contain the totally symmetric irreducible representations of the point group of the system. This is usually labeled as the A sub 1.
In molecular rotation, the simplest molecule to have shown rotation is a diatomic molecule. Its energy is defined as E rot is equal to J multiplied by J plus 1 multiplied by H bar divided by 2I, where E rot is the rotational energy, J is the quantum number, which is also used in defining the angular momentum of the molecule, H bar is the reduced Planck constant, I is the moment of inertia. We can further define the equation, which is shown in the screen. The formula for the calculation of rotational energy can be used for linear polyatomic molecules. But how about the nonlinear molecules? For the rotational energy of nonlinear molecules, It is first classified based on the moment of inertia for each axis of rotation. There are four types of nonlinear molecules, which are spherical top, oblate symmetric top, prolate symmetric top, and asymmetric top. Presented on the screen is the corresponding condition in which a molecule have to identify its type. So when can we use the moment of inertia? It can be used in calculating the constants A, B, and C, which is necessary in calculating the rotational energy of a molecule as shown in the table. Rotational spectroscopy is a type of spectroscopy that measures the energies of transition between quantized rotational states of molecules in gas phase. This technique provides information on the structure and chemical bonding of molecules and crystals by measurement of wavelengths of microwave emitted or absorbed by the sample. This technique is useful in calculating sizes of diatomic molecules. Shown in the screen is the energy changes between the energy states. But how are these values obtained? It was obtained by the formula delta B is equal to 2B multiplied by J plus 1. The formula was then used for calculating the constant to be used in getting the changes in energies of transition. Now, let us discuss how the rotational spectroscopy identifies the size of diatomic molecules. From previous discussion, we have a formula for getting the constant V, and we also have a formula for getting the moment of inertia. Through algebraic manipulation, we can obtain a formula in terms of the internuclear distance, which is the square root of h bar raised to 2 over 2b multiplied by mu. It is said that the internuclear distance assumes the size of the molecule. Now, the successful applications of rotational spectroscopy are determining the structure and the geometry of ozone, identifying and qualifying the trace gases in the atmosphere such as methane, nitrous oxide, and the chlorofluorocarbons, studying the dynamics and interaction of molecular complexes such as water dimers, and detecting and characterizing molecules in interstellar clouds such as ammonia, water, carbon monoxide, and formaldehyde.
In this part of the video, we'll discuss vibration in the molecules. A molecule has a translational and rotational motion as a whole, while each atom has its own motion or vibrational motion. This picture shows the translational motion when the whole molecule moves uniformly in one direction, and this figure shows the rotational motion for nonlinear and linear molecules when the molecule moves circularly in a fixed orbit. There are two types of vibration: stretching, or the changes in the interatomic distances along the band axis, and bending, or the changes between the bonds in a molecule. Stretching can be categorized into two. Symmetric stretching is when two atoms simultaneously moves away and towards the central atom, while asymmetrical stretching is when one attached atom simultaneously moves away and while the other moves towards the central atom. Next is bending, which can be categorized into four. Scissoring is when two atoms moves toward and away from each other. Rocking is when two atoms acts like a pendulum on a clock. Wogging is when two attached atoms moves from side to side, and twisting causes a change in the angle between the planes of two groups of atoms. Now, let's move on to the normal modes of vibration, or the independent and orthogonal motions of each atom in a molecule. The table shows the overview of the degrees of freedom, where the vibration degrees of freedom also shows the calculation for the normal modes of molecules. For nonlinear molecules, it is 3n minus 6, and for linear molecules, it is 3n minus 5. As a practice problem, let's calculate the normal modes for acetylene and ethane. For acetylene, a linear molecule, it is 3 times 4 minus 5 is equals to 7. For ethane, a nonlinear molecule, it is 3 times 8 minus 6 is equals to 18.
Now, we know about how the plot of the ideal harmonic oscillator forms a parabola to where the potential energy increases as it goes to infinity at either direction of displacement. And particle cannot be found where its potential energy is infinite. Therefore, not all wave functions and not all energies are allowed. And should vibrational motion be quantized? Given below are the formula for quantized energies of the harmonic oscillator, where in the first part, the orange V is the vibrational quantum number, while the second part, V is the frequency. Kf is the force constant and m is the mass. These formulas are used in computations. This tells us that the vibrations act as an ideal harmonic oscillators that have certain wave functions and certain quantized energies as shown in this figure. Now, for the gross selection rules for vibrational transitions focuses on this particular statement. For a vibrational transition to occur as a result of absorption or emission of a photon, the electric dipole moment of the molecule must change during the vibration. This means that in order for a molecule to shake the electromagnetic field into oscillation, it should have an electric dipole moment that oscillates as the molecule vibrates, which can be seen in this figure right here. So this rule only requires a change in dipole moment, possibly from 0. And given in this equation, it can be from 0 to positive 1 or 0 to negative 1, not necessarily a permanent dipole. So different molecules can be considered to be infrared active or inactive. We say a molecule is infrared active if there is a change in dipole moment, whereas infrared inactive is the opposite. Let's understand the rules with methane as our molecule. Given here are the different normal vibrational modes of methane, having arrowheads showing the direction of oscillation or vibration. We know that having a dipole moment tells us that methane is infrared active. Therefore, methane can be detected in vibrational spectroscopy, which results into this spectrum. Given the spectrum here, we can identify that at 1306 and 3019 reciprocal centimeters, there are strong peaks of carbon to hydrogen bending and carbon to hydrogen stretching, respectively. Notice also that bending modes are in the lower wave numbers as they are less stiff than stretching modes that are in higher wave numbers.
Now, let's consider vibrational spectroscopy of diatomic and linear molecules. Vibration spectrum of diatomic molecules are simple since it only considers stretching motion, while triatomic linear molecules has three motions. Vibration is classified to be an ideal harmonic oscillator when molecules move back and forth from their center of mass. The force that opposes the motion is equally proportional to the equilibrium energy. Here's an example potential energy curve of an ideal harmonic oscillator with an equation shown here. The vibrational levels are equally spaced with a constant energy difference. It also doesn't have a dissociation energy until the potential energy level reaches infinity. However, real molecules do not operate in ideal systems and are considered anharmonic. We have here a comparison between harmonic and anharmonic curves. We can see that the curve is close to ideal at low energies, but it's wider at higher energies. At high energies, molecules have adequate energy to move way too far from each other and not to go back. This is the stage where molecules get dissociated, and the energy responsible for this phenomenon is the dissociation energy. Real molecules has a different consideration for its energy, and it's given by the Morse potential as shown here, where d sub E is the dissociation energy measured from the bottom of the curve, and A is a constant and can be obtained by the following equation. Zero-point energy is defined as the energy possessed by a molecule when the potential energy equals zero, and it's the actual energy level where the dissociation energy is really measured from. At this point, molecules must vibrate even at 0 Kelvin, and no atoms are resting at this point. The dissociation energy measured starting from the zero point is given by the equation shown here. Morse potential is quantized, and it only allows us to quantify anharmonicity or the amount of non-harmonic behavior of the molecule. This part of the video discusses the symmetry considerations for vibrating molecules. We know that all molecules have an assigned point group to classify if there's symmetry. However, it only considers that the molecule is in a fixed position. A molecule's symmetry is based on its equilibrium atomic position and is the basis for understanding its behavior. All normal modes of molecules oscillate at a fixed equilibrium position. In considering vibrations, Movements of atoms in most molecules are small and do not significantly change the position from the equilibrium state, which tells us that group theory and symmetry are still applicable when considering molecular vibrations. We have here an example of a water molecule. It has an identity element E with a C2 rotation. It also has mirror planes both vertically and horizontally, which also equates to A1. We find that even if the molecule were to vibrate, it will still show the same symmetry C2V. And from this, we can note that group theory is still applicable in describing the symmetry of vibrating molecules.
Moving on to the vibrational spectroscopy of nonlinear molecules, their vibration in contrast to linear molecules varies significantly due to their difference in symmetry that determines the number of vibrations in the molecules as well. As discussed a while ago, for nonlinear molecules, the vibrational degrees of freedom is now 3n minus 6. Hence, we can infer that they have more freedom to move or vibrate. There's also a difference in rotation of the molecular axis that changes the configuration of the molecule that may or may not result to vibrational modes. As an example, ammonia molecule has a molecular geometry of trigonal pyramidal. It has four known vibrational modes that are known to be all IR active. And for V1, all the NH bond stretches outward simultaneously and symmetrically, inducing change in the size of the molecule. For V2, a bending stretch is observed where there is an alteration in the H and H bonding. And for both V3 and V4, a symmetrical stretch can be observed where two NH bonds have the same stretch direction while the remaining compress in a season fashion. As the nonlinear configuration gives room for complex vibrations, these characteristics are analyzed using spectroscopic techniques. Moving on to the last topic, the distinction for Raman spectroscopy is that it focuses on the light scattered by a sample rather than the light absorbed or emitted by the sample. It is a non-destructive technique that can be used to analyze the chemical structure of the sample. It uses laser as the light source for the sample and lenses that reflects the scattered light and a detector that produces the Raman spectra. So in principle, the scattering of light is facilitated by Rayleigh and Raman scattering. So Rayleigh scattering is concerned about the elastic collisions of molecules or photons. As the light passes through the sample, tiny amounts of light or photons is scattered in an angle from the sample that also comes off from the sample at a certain angle. This light has the same frequency as the incoming light that is inversely proportional to the fourth power of its wavelength. Meanwhile, Raman scattering is the scattering of light and the change in frequency that focuses on the inelastic collisions. The energy changes the outgoing photons that can be inferred as a change in quantized energy as well. In here we can see that the anti-strokes Raman scattering is where the wavelength of the laser is larger than the wavelength of the scattered light and vice versa for the strokes of Raman scattering. So before we end this discussion, here's an example of a Raman spectra. This is a Raman spectra of a tetrafluoroethylene molecule. The two scales on the abscissa spectrum is where the visible and red light were used. The largest peak exhibits the Rayleigh scattering, while some of the photons appear at lower frequencies. The strokes and antistrokes of the spectra meanwhile showed a modified mirror image where the antistrokes are just lowered in intensity. And that would be all for the brief discussion about the rotational and vibrational spectroscopy. Here are the references used in